There are many end-use systems. There is the ATP-PCR system, the glycolytic system, and the oxidative end-use system. The ATP and creatine phosphate system, also called phosphocreatine or PCR for short, make up the ATP-PCR system. PCR is broken down releasing a phosphate molecule for an energy, which is then used to rebuild ATP. ATP is rebuilt by adding a phosphate molecule to ATP in a process called phosphorylation. There is an enzyme that controls the breakdown of PCR, and it is called creatine kinase. The ATP-PCR energy system can operate with or without oxygen, but because it doesn't rely on the presence of oxygen, it is said to be anaerobic. During the first 5 seconds of exercise, regardless of intensity, the ATP-PCR is relied on almost exclusively. ATP concentrations last only a few seconds, with PCR buffering the drop in ATP for another 5 to 8 seconds or so. Combined, the ATP-PCR system can sustain all-out exercise for 3 to 15 seconds, and it is during this time that the potential rate for power output is at its greatest. If activity continues beyond this intermediate period, then the body must rely on another energy system to produce ATP. Glycolysis literally means the breakdown or lysis of glucose, and consists of a series of enzymatic reactions. Remember that the carbohydrates we eat supply the body with glucose, which can then be stored as glycogen in the muscles for later use. The energy product of glycolysis is pyruvic acid. Pyruvic acid can then either be funneled through a process called the Krebs cycle or converted into lactic acid. Traditionally, if the final product was lactic acid, the process was labelled anaerobic glycolysis, and if the final product remained as pyruvate, the process was labelled aerobic glycolysis. However, oxygen availability only determines the fate of the end product, and is not required for the actual process of glycolysis itself. In fact, oxygen availability has been shown to have little to do with which of the two end products, lactate or pyruvate, is produced. Hence the terms aerobic meaning with oxygen and anaerobic meaning without oxygen become a bit misleading. Alternative terms that are often used are fast glycolysis if the final process product is lactic acid, and slow glycolysis for the process that leads to pyruvate being funneled through the Krebs cycle. As its name would suggest, the fast glycolytic system can produce energy at a greater rate than slow glycolysis. However, because the end product of fast glycolysis is lactic acid, it can quickly accumulate and is thought to lead to muscular fatigue. It may take more than 1 hour for lactic acid levels to return to their pre-exercise level. The oxidative system consists of 4 processes to produce ATP: slow glycolysis or aerobic glycolysis, the Krebs cycle or citric acid cycle, the electron transport chain, or beta oxidation. Slow glycolysis is exactly the same series of reactions as fast glycolysis that metabolizes glucose to form 2 ATPs. The difference, however, is that the end product, pyruvic acid, is converted into a substance called acetyl coenzyme A, rather than lactic acid. Following glycolysis, further ATP can be produced by funneling acetyl coenzyme A through the Krebs cycle. The Krebs cycle is a complex series of chemical reactions that continues the oxidation of glucose that was started during glycolysis. Acetyl coenzyme A enters the Krebs cycle and is broken down into carbon dioxide and hydrogen, allowing more than 2 ATPs to be formed. However, the hydrogen produced in the Krebs cycle plus the hydrogen produced during glycolysis, left unchecked, would cause cells to become too acidic. So hydrogen combines with 2 enzymes called NAD and FAD and is transported to the electron transport chain. Hydrogen is carried to the electron transport chain by another series of chemical reactions, and here it combines with oxygen to form water, thus preventing acidification. This chain, which requires the presence of oxygen, also results in 34 ATPs being formed. Unlike glycolysis, the Krebs cycle and the electron transport chain can metabolize fat as well as carbohydrates to produce ATP. Lipolysis is the term used to describe the breakdown of fat into more basic units of glycerol and free fatty acids. Before these free fatty acids can enter the Krebs cycle, they must undergo a process of beta oxidation, a series of reactions to further reduce free fatty acids to acetyl coenzyme A and hydrogen. Acetyl coenzyme A can now enter the Krebs cycle, and from this point on, fat metabolism follows the same path as carbohydrate metabolism. So to recap, the oxidative can produce ATP through either fat fatty acids, or carbohydrate, glucose. The key difference is that complete combustion of a fatty acid molecule produces significantly more acetylcoenzyme A and hydrogen, and hence ATP, compared to a glucose molecule. However, because fatty acids consist of more carbon atoms than glucose, they require more oxygen for their combustion. So if your body is to use fat for its fuel, it must have sufficient oxygen supply to meet the demands of the exercise. If exercise is intense and the cardiovascular system is unable to meet the supply cells with oxygen quickly enough, carbohydrates must be used to produce ATP. Put another way, if you run out of carbohydrate stores, as in a long duration events, exercise intensity must reduce as the body switches to fat as its primary source of fuel. Protein is thought to make only a small contribution, usually no more than 5%, to energy production, and is often overlooked. However, amino acids, the building blocks of protein, can be either converted into glucose or into other intermediates used by the Krebs cycle, such as acetylcoenzyme A. Protein may take a more significant contribution during the prolonged activity, perhaps as much as 18% of total energy requirements. The oxidative system as a whole is used primarily during rest and low intensity exercise. At the start of exercise, it takes about 90 seconds for the oxidative system to produce its maximal power output, and training can help to make this transition earlier. Beyond this point, the Krebs cycle supplies the majority of energy requirements, but slow glycolysis still makes a significant contribution. In fact, slow glycolysis is an important metabolic pathway even during events lasting several hours or more. Each of the three energy systems can generate power to different capacities and varies within individuals. Best estimates suggest that the ATP PCR system can generate energy at a rate of roughly 36 calories per minute. Glycolysis can generate energy at only half as quickly, at about 16 calories per minute, and the oxidative system has the lowest rate of power output at about 10 calories per minute. The capacity to generate power of each three energy systems can vary with training. The ATP, PCR and glycolytic pathways may change by only 10 to 20% with training. This is good for sprinters because it will increase the amount of energy they can produce in a minute. The oxidative system seems to be far more trainable, although genetics play a limiting role here too. VO2 max, or aerobic power, can be increased by as much as 50%, but this is usually in untrained sedentary individuals. This is good for marathon runners because it will increase their aerobic endurance, meaning that they will be able to run for a greater amount of time. All the energy system facts were taken from www.sportsfitnessadvisor.com.